Hi, everyone. Maybe we slowly start. And anyway, I first wanted to talk about logistics, so maybe then some more people come. Okay, so welcome to the exercise class on the advanced topics in quantum information theory. So this is the first exercise class, and first few points about like what was going to happen. And so I leave the motivation and why this course is important and what exactly we're going to cover to the lecture, which will happen just after this exercise class. So here I'll just cover the logistic parts which are important to the exercise class. Okay, and then after that we'll do very short recap of some important concepts from quantum information theory, which will appear and will be useful to know before we dive in further into this course. Okay, so let me introduce myself. I'm Nuriya. I'm a third year PhD student in quantum information theory group. And yeah, so whenever during the course, you're free to contact me by the following email that you can see on screen with any questions concerning the exercise sheets or the course or the exam, whenever about whatever you feel you're uncomfortable with. So all exercise classes and all lectures as well will be recorded and posted on YouTube, and the links will be also posted on Moodle. So the protocol for exercise sheets is as follows. So on Tuesday each week, the exercise sheet number N, let's say, will be posted. On Wednesday, we will discuss this exercise sheet, and I'll give you some hints and the directions that you need to take in order to solve the exercise. And on Monday, something I didn't add here. So on Monday next week, solutions are posted. So you're not required to give in the exercises, just ask questions in case there is something unclear with the solutions, or if you have an alternative solution and you're not sure if it's right or not. Okay, then yeah, also you're not required to attend exercise classes. You can watch them on YouTube whenever you like. So this is not a requirement to pass the course. However, like the questions which will be included in the exercises are also relevant for the course and for the exam as well. Also, the last one, but not the least, is please feel free to speak up if something is not clear during the class. Don't worry, you can just directly interrupt me and turn on your mic, maybe your video, and then just ask the question directly. You can also post the questions in the chat, and I will not constantly monitor the chat. I will only check it out periodically. So if you ask a question in the chat and I don't answer immediately, it just means that I haven't seen it yet, but I will check it out at some point. Okay, are there any questions about the logistics of the course, like concerning exercise classes? Okay, seems no questions. So let us then start with our short recap. Okay, so all the topics I'm going to talk about are probably something that you already heard in quantum information theory or quantum information processing, or also possibly your quantum mechanics course. So this is just in order for you to revise the most important points, mostly technical points, which will be used in the course. So, okay, so we will start with unitary and Hermitian operators. So what is a unitary operator? So unitary operator, so we call an operator in Hilbert space H. And we call it a unitary if it is its own inverse. Sorry, if it's conjugate transpose, it's inverse. So if u dagger equals u dagger u equals identity. This is a unitary operator. And let's give it another name. Let's say that A is also an operator in H. Then if A is equal to its own conjugate transpose, then we call A Hermitian operator. And these operators, as you probably know, have a special meaning when it comes to its usage in quantum theory. So for example, the quantum evolution is described by a unitary operator, in particular the evolution given by the Schrödinger equation. And also we describe the observables in quantum theory as Hermitian operators. And also because of the property that Hermitian operators have, which is that all of their eigenvalues are real, which is a consequence, of course, of the fact that the Hermitian operators are equal to their conjugate transpose. Okay, so a few properties which are a part of the exercise sheet. So first, the operator exponential. So we can define an operator exponential, e to the power a, just as Taylor series of the exponential yeah, and this is in writing this operator exponential is again important when we write the solutions or the evolution for the Schrödinger equation. And it has the following properties. So first, if we take its conjugate transpose, then writing out the exponential in this series form, we can show that it is just the exponential of the conjugate transpose of A. And the second more interesting property is that if we take the exponential of the sum of two operators, A and B, then if A and B commute, then we can just write it as exponential of A by exponential of B. This also can be shown by just writing out the this exponential as Taylor series and then using the binomial formula. Okay, And the consequence of these two properties is that if we write an operator u, which is the operator which is the exponential of IH, where H is Hermitian, then it is a unitary. So as you remember, for example, in quantum theory, one of the observables that we can look at is the total energy of the system. And the and usually to this observable, the operator that we assign is the Hamiltonian of the system, which describes the dynamics of the system, and also which appears in the Schrödinger equation. And then because the solution to the Schrödinger equation is essentially given, the time evolution is given by the operator e to the power IHT, this property guarantees that this evolution is a unitary if the Hamiltonian is Hermitian, which it is by definition. Okay. This also works backwards, as in if A, let's call it H maybe. So if H, okay, so if U is a unitary, then there exists a Hermitian operator H such that U equals e to the power IH. So, which in physical terms means that if we have some unitary evolution of the system, then we can always find a Hamiltonian which governs that evolution. However, the important point to make here is that the choice of this Hermitian operator H is not unique. Yeah, so one of the ways to see it is just to add just add a constant component with the identity matrix multiplied by 2 pi I, and then e to the power 2 pi I would give us 1, and then essentially that will give us the same unitary U. So it's important to remember that this choice is not unique. So how does one show this?
Excuse me.
Yes.
Is it not unique up to a phase, or could there be more than one Hermitian operator that give the same but not up to a phase?
Yes, I think there can be, but just I gave the example with the phase because it's the easiest way to see how this is not unique, but otherwise, yeah, maybe there can be several H's which describe the same U.
Okay, thank you.
Okay, so the hint to show this is just to write U in its diagonal form. So this is also a trick that comes from, of course, linear algebra, where the easiest way to consider operators is to consider their diagonal form. And also, I guess the important remark to make here is that, yes, we're talking about operators in Hilbert space, which are a somewhat abstract model for observables or evolution. But what we also often mean by this is the representation of this operator in a particular basis. So each operator with the respect to given basis can be written out as a matrix. And And in thinking in these terms, it's then easier to think about this analogy to linear algebra. And in linear algebra, we know that every unitary matrix we can write down in its diagonal form by performing a change of basis. And so this is exactly what we do here. So we know that we can rewrite the U in its diagonal form via the change of basis, which is governed by another unitary, W. And its diagonal form, the diagonal form of the unitary also has to be unitary. So it yes, so it also has to be unitary. So D dagger has to give us the identity, which means that all the diagonal elements have to have modulus 1. So they can all be written as just some phases. So e to the power I alpha 1, e to the power I alpha 2, and so on, e to the power I alpha n. Okay, and having written it like that, we can claim that the Hamiltonian, the operator, the Hermitian operator H, which can be understood as a Hamiltonian governing this evolution, is then written as just W, then this diagonal matrix with diagonal entries alpha 1, so on alpha n, W dagger. And then one can show that e to the power IH is exactly U. Okay, so the next thing that we can talk about is what happens if the operator, let's call it V, is both Hermitian and unitary. Then it's quite easy to show that first V squared equals identity. And also its eigenvalues can only be plus and minus ones. So this is just a particular case of an operator. Okay. Then one thing which is a bit more important in this course is this particular property that two operators have if they commute. So suppose that A and B are Hermitian operators. And also they commute. So the commutator of AB, which I'm just reminding you, is AB minus BA equals 0. Then we can claim the following, that there exists a basis where both A and B are either diagonal or block diagonal. Okay, and this I will show because this it's quite easy to show and it's going to be quite important in this course. So consider an eigenbasis of an operator A. Let's call it psi I. Okay, maybe I'll call it a bit differently. count for things. So let's call it psi I, and for each I will have the indices of psi I going from 1 to ki. This I do this to account for the case where the spectrum of the operator A is degenerate. This means that for one eigenvalue, we can have we have several corresponding eigenvectors. So this, for example, happens when if you consider A as the Hamiltonian, which represents the energy of the system, and the Hamiltonian of the system can be degenerate. So it can be so that several eigenstates of the system correspond to the same energy of the system. So hence this superscript here. And then the eigenvalue corresponding to each of these eigenvectors from psi I1 to psi I ki is lambda I. So maybe I write it like this: psi ij equals lambda I psi ij for j from 1 to ki. Okay, so then for all such psi i's, we have that AB psi ij equals, here we use the commutation relation, so we have BA psi ij. Then we apply A to the eigenstate. Here we get lambda I B psi ij. So essentially this means that A acting on a vector B psi j equals lambda vector B psi ij. This means that B psi ij is actually an eigenvector of A. With the eigenvalue lambda I. Okay, so, and then there are, of course, two cases. So the first is when lambda I is non-degenerate, which means that essentially ki equals 1. So there is only one eigenvector corresponding to the eigenvalue of lambda I. Which means that B psi I equals mu I psi I. So if there is only one eigenvector corresponding to this eigenvalue lambda I, then B psi I has to be a multiple of the vector psi I, which means that psi I is an eigenvector of B. And the second option is that lambda I is degenerate. So then there are more vectors associated to lambda I, but since B psi I is an eigenvector of A, which is associated with this eigenvalue lambda I, then it can be written as a superposition of all eigenvectors corresponding to that eigenvalue. So essentially, it can be written in the subspace, which corresponds to that eigenvalue. So B psi I is equal to superposition of this psi I j's. Yeah, J belongs to to this subspace essentially. So we can see in this case as B acting internally in the subspace. So what essentially this means is that all the eigenvectors of A are the eigenvectors of B if they correspond to a non-degenerate eigenvalue, and if we have a degenerate eigenvalue, then still B can be the eigenvector of B can be written as a superposition of the vectors in that subspace, which means that, for example, in a case where all eigenvalues are non-degenerate, the eigenbases of the operators A and B simply coincide. So then both A and B can be written in that basis diagonally, simultaneously. If there are degenerate eigenvalues, of course the form of the matrix becomes a bit more involved. So if we have a basis in which A is diagonal, so A has a form that there are zeros here, and there is something on a diagonal, B can be written in that basis as in a block diagonal form. So in the subspaces which correspond to a degenerate lambda i's, we can still write B as a superposition of the vectors belonging strictly to that subspace. So we have this blocks on a diagonal. Yeah, so this is an important property to keep in mind when two operators commute. This also gives us a bit of more feeling of what happens when these degenerate cases come up. They're usually not so comfortable to deal with, but we have to keep them in mind because this is something that occurs physically in the systems. Okay, then the next important topic, which I'll only cover briefly because I imagine that you already heard and practiced it a lot in quantum information theory and or quantum mechanics, but I think it's still worth mentioning. So this is the tool of trace and partial trace. So suppose that we have an operator A in a Hilbert space H. Then the trace of this operator is defined as sum over J, J, A, J, where J is the orthonormal basis in the Hilbert space H. And coming back to our matrix representation of U, we would have that if A is written as a matrix, then it's in some orthonormal basis, and H, then trace of A is just the sum over its diagonal elements. So there are certain properties which this trace operation has, which is that it is linear, it is cyclic, and it is basis independent. So I expect that you'll probably have seen these properties, so I will not go much into them. If you want to recap that, just look at the exercise sheet and try to like prove these properties there. And the next operation, which is extremely relevant for the purposes of quantum information theory, is what is called a partial trace. And a partial trace is defined for a system which consists of two subsystems. And it essentially it is first a generalization of marginal distributions in classical probability theory. The same as when we talk about density matrices as a description of a quantum system, we kind of keep in mind that density matrices was a generalization of like putting a classical probability distribution on top of the like on top of the quantum theory. As in, like when you talk about the density matrix, then you basically give yourself a way to answer a question. Oh, I prepared a system in a state 0 with probability 1/2, and I prepared the system in a state 1 with probability 1/2. How do I write? And then it's like I forgot which one I exactly prepared. So how do I write the state of the system in that case? And I just say, okay, then you write it as the identity matrix over 2, which is the density matrix of the state. But starting to talk about that, then we also want to talk about, okay, I have this kind of description of it of two systems jointly, but then I also wanted to look what happens if, for example, I measure the first system and then I forget about that result. What is the state of the first system? And this corresponds to the operation. This also classically, as I said, it corresponds to looking at the marginal distributions. And quantum mechanically, this corresponds to the operation of partial trace. So suppose that we have rho B, which is a density matrix, on the Hilbert space, which is a tensor product of Hilbert spaces of the systems A and B. And then I just want to look at the state on the system A alone. So I need to trace out the system B. And this operation corresponds to the following. So we essentially don't apply anything on the A part, and then just do the usual trace on the system B. The J's are again just the orthonormal bases, but now in HB. And one can also show that this operation is indeed valid. It indeed maps density matrices to density matrices, which means that it preserves, which means that the object that we get after tracing out a density matrix is semi-positively defined. Then, Hermitian, and so on. Okay, so I will not talk more about it. There is a bit more in the exercise, but please revise these things if you feel uncomfortable with them. And the final thing I would like to talk about is wait, my pencil suddenly stopped working. Yeah, now it's fine. The final thing I want to talk about are thermal states. Maybe I start a new page. So suppose that we have a system with the following Hamiltonian, H, which we just write in the diagonal form. So sum over I, EI, II, where EI are essentially the energies which correspond to each of the basis states, I, in which this Hamiltonian is written. And suppose that the system is kept at the temperature T. Sorry, seems that my pencil is acting weirdly today. Okay, so the system is kept at temperature T. And for this temperature, we can define a certain state, which we'll call the thermal state. I'll give the intuition for this in a moment. So this is essentially the following states, the density matrix of which can be written as e to the power minus h over kt over z, where z is just the normalization of this exponential. So z is sum over I. So first it can be written as trace of e to the power minus h over kt, which is sum over I e to the power minus ei over kt. So z is also called partition function. Okay, so what is the state exactly? So you probably have seen this type of states if you did thermodynamics or statistical physics. The idea here is that, so suppose that we have a certain system with the energy of which is described by this Hamiltonian, or a system which can take a particular energy levels, right? And then we take the system and put it at temperature T. And you can think about it as also, for example, in terms of classical thermodynamics, where you have a gas, and the molecules of the gas can occupy certain energies, or have certain velocities, for example. And then you take that gas and put it at a temperature T. And the temperature T phenomenologically defines how, what is the energy of each molecule, as in like it's a characteristic energy for each molecule. And then of course, the higher the temperature is, then the higher level the molecule is able to occupy. So for example, a good example would be also a gas of molecules which is put in a gravitational field. And then if this gas has a certain temperature, this temperature defines essentially how high the molecules of the gas can go. So you probably all notice that when you go up up in the mountains, the number of molecules per volume decreases. So you start, for example, you start breathing. You have to breathe more often because there is not enough oxygen in the way you usually breathe. And this is exactly, and the distribution of the molecules over this difference in the potential, which is given by the gravitation, is exactly described by so-called Boltzmann distribution, which is kind of, what's up with my pencil? This is really annoying. So the Boltzmann distribution is also shows that the amount of so the concentration of molecules at a particular height is proportional to the e to the power minus mgx, which is the potential of the gravitational potential of the particle at the height x over kT. So if you think about it physically, it kind of makes sense that the higher you go, then kind of the more potential energy the molecule needs to have to be at that height, and hence, if that energy is much larger than kT, which is kind of the characteristic energy of the molecule in that gas, then the less molecules will be able to achieve that. And so that's kind of that distribution is exponential. So Boltzmann distribution, which tells us that it's proportional to E minus E over kT. And here for the quantum states, we can kind of using the same analogy of distribution of the statistical distribution over levels, we can introduce the same state, which would give us kind of the different population for the for different levels I with energies EI. Okay, so so K here is a Boltzmann constant. And the other the other convention that is often used is that always writing 1 over kT is a bit cumbersome. So we often just write it in terms of this variable beta, which is 1 over kT. And then, for example, tau of t becomes e to the power minus beta h over z. Okay, so in the exercise sheet, you're asked to show one particular property of the thermal states, which is that thermal states are composable. In the case where the system is governed by the Hamiltonian, where these two subsystems don't interact. So for example, if we have a Hamiltonian of two non-interacting systems, which we label as A and B, then we can show that the thermal state tau AB at a temperature T can be written as a tensor product of the thermal states on the subsystems A and B individually. Okay, so the first thing that we have to kind of consider to write out the thermal state for the joint system of A and B is what are the eigenvalues of this Hamiltonian HAB? So we can write the Hamiltonian HMB inserting the diagonal forms of the Hamiltonians HA and HB. So we just choose the bases in A and B, which correspond to their Hamiltonians being diagonal. So for system A, I call the eigenvalues EIA. And for the system B, I call the eigenvalues EBJ. This means that because these two systems conveniently don't interact, this means that we can choose the eigenfunctions. So, okay, maybe I call them eigenstates to be more consistent. So the eigenstates IA tensor product GB going over O and I and J. And it's easily seen that indeed these are the eigenstates, and the eigenvalues which correspond to these eigenstates are EIA plus EJB. Okay, then we are ready to write out our thermal state at temperature T. So on the top, we have e to the power minus beta, our Hamiltonian, and down there we have the partition function, which is because we just found out the eigenvalues can be just written as e to the sum over I and j, e to the power minus beta, EIA plus EGB. Okay, for the top term, we actually can use something that we've seen as a property of the operator exponential, that if we are looking at the exponential of the sum of the two operators, we can safely separate it if the operators commute. And here, because we have HAA acting on a subsystem A and HB acting on subsystem B, these two actions are independent, and so these two operators trivially commute. So it doesn't matter in which order we apply them, which means that we can just write this as 1b by minus beta 1a HB over, and here we can also separate the sum. Okay. Yeah, because here in the first term we have tensor product by identity. It just turns into e to the power tensor product by e to the power to identity, which gives us sorry, no, that I'm doing it wrong. So essentially, if we have this tensor product by identity in the exponential argument, then this just turns into e to the power minus beta HA tensor identity on B. So this can be just shown again by writing out this as the the Taylor series of the exponential. And here we have similarly just identity on A, e to the power minus beta hb. And here we have partition function on A, partition function on B. Okay, and so in the end, what we get is ZA tensor product e to the power minus beta hb over zb, which is exactly the thermal states on A and B. Okay, so we see that the thermal state has this property that if we write it for a composition of two systems which do not interact, then it can be written as just the tensor product of the thermal states on each of the systems individually. And of course, this is easily generalized for the case of n systems. So for example, if you have n systems which do not interact, and you want to write a thermal state on that n systems jointly, you can just write a thermal state for each system individually and take their tensor product. So this was a composability feature of thermal states. Okay, so I think that more or less covers the first exercise sheet and also kind of the most important quantum mechanical linear algebra related prerequisites that you would need to have for the course and also for the first lecture. So yeah, so if you have any questions, please shoot at me.